Welcome to Wisdom Docs. Settle in. Let the lights go low, let your shoulders drop away from your ears, and let your breathing slow to the pace of a tide going out. Tonight we are going to travel somewhere very far away, somewhere very hot, and somewhere very strange. But you are not going there. You are staying right here, warm and safe, wherever you happen to be lying. The place we are visiting only comes to you through the sound of these words, and words are soft things. So let them wash in slowly, one after another, like small waves against a wooden dock, and let the harder edges of the day float off with them. There is a pool of water I want you to picture. It is a small thing, really, no bigger than a garden pond, sitting out under a sky the colour of hammered brass. And it glows. It glows a green so bright and so unnatural that the first time you saw a photograph of it, you might think someone had spilled paint, or dropped food colouring, or tampered with the picture. It is the green of certain old glass bottles held up to a lamp. It is a green that does not belong to living things. And around its rim, the ground is stained yellow, the yellow of egg yolk, of powdered mustard, of a bruise going pale at its edges, and orange, and a chalky, blistered white, all crusting together in ridges and terraces, like a cake left too long in an oven that never turned off. Now lean a little closer, in your mind, though not too close. That water is boiling. Not warm. Not merely hot the way a bath is hot. Boiling, or very near it, with little threads of steam curling up off its surface and a faint, rotten, sulphurous smell riding the air. And here is the part that is hard to hold in your head. The part we will keep coming back to tonight, because it is the strange heart of this whole story. That water is not just boiling. It is also saltier than the sea, saltier than any sea, so heavy with dissolved minerals that it feels almost oily. And it is acid, deeply, ferociously acid. You have probably heard of pH before, that number chemists use to describe how acidic something is. Think of it as a simple ladder. Pure water, the kind that comes out of a clean tap, sits right in the middle of the ladder. At a 7, comfortable and neutral. Lemon juice is down around a 2. Battery acid, the sort that eats through metal and cloth, sits near a 0 at the very bottom rung. That is as low as most people ever imagine the ladder goes. 0, the bottom. The water in some of these pools goes below 0, below the bottom rung. There is no lower rung on the ordinary ladder. And yet here is water that has climbed underneath it, water so acidic that the usual scale runs out of numbers and the chemists have to write a minus sign in front of the reading. It is one of the most acidic natural waters ever measured anywhere on the face of the earth. Boiling, saltier than the ocean, acid enough to run off the bottom of the chart. All at once, in the same little glowing green pool, under that brass-coloured sky. And nothing lives in it. Nothing at all. Sit with that for a moment, gently, the way you'd sit with a curious thought just before sleep. Because it runs against everything we are usually told about this kind of place. You know the story by heart, even if you've never named it. It's the story where nature is unstoppable, where life is a kind of stubborn miracle that wriggles into every crack and corner, where, and you can almost hear the confident voice saying it, life, finds a way. We love that story. It is a comforting one. It tells us that no matter how harsh the room, something will always be at home in it. But this pool does not care about that story. This pool is a quiet, boiling contradiction to it. And that contradiction is exactly why, tonight, we are not going to ask the usual question. We are not going to marvel at how life clings on in impossible places. We are going to ask the far more interesting question. the one that scientists actually travel across the world to this exact spot to answer. Not how does life survive here? Where does life finally give up? Because that is what this desert really is. Not a curiosity, not just a pretty hellish oddity for a travel photograph. It is a laboratory, an open-air, sun-blasted, salt-crusted laboratory where researchers come to find the outer edge of life itself, the very boundary, the line beyond which the fabric of living things simply cannot hold together no matter how hard it tries. And when you're hunting for a line like that, you don't go somewhere gentle. You go to the harshest room you can find, and you watch very carefully for the place where the last flicker goes out. This desert is that room. And the flicker going out, or refusing to go out, is a mystery that two teams of scientists would end up arguing over, publicly, in the pages of serious journals, reaching opposite conclusions about the very same water. But we'll come to that. We have all night, there's no hurry at all. Let me set the place beneath you first, so you know where you're floating. This is called the Danakil Depression. Say it slowly to yourself, Danakil. It lies in the northeast of Ethiopia, spilling over toward Eritrea and Djibouti, in a wider region that geologists call the Afar Triangle, or the Afar Depression. You can think of the whole thing as an enormous shallow bowl pressed down into the surface of the continent, a bowl so wide you could never see across it, its floor cracked and salted and stained. And the word depression there is not about mood, it is about height, or rather the lack of it. This is a low place, one of the lowest patches of dry, exposed land anywhere in the world. To picture how low, forget mountains for a moment and think about the sea. Think about standing at the ordinary shoreline, where the waves come up and touch your feet. That line, that height, is what we call sea level, and almost everywhere you have ever stood in your life has been above it. Now imagine walking downhill from that shoreline, not into the water, but into the land, down and down, until the ground beneath your boots is lower than the waves you left behind. Down past 30 meters below the sea, past 50, past 100, until near a great salt flat here called Lake Asale, sometimes also called Lake Karum, you are standing on ground that sits roughly 116 meters beneath sea level. 116 meters. That's a tall building's worth of downward, a deep, deep dent in the skin of the planet, and the sea is not there to fill it. There is only salt and heat, and that brass-coloured sky pressing down. If you could somehow cut a channel from the distant coast, the ocean would come pouring in and drown this whole basin. And hold on to that thought loosely, because before the night is over, we are going to find that the ocean has every intention of doing exactly that, in its own slow and patient way. But for now, the bowl sits empty of water and full of everything else, low, dry, and blazingly, relentlessly hot. Here is how hot. There is a spot in this depression called Dallol, that green glowing pool I set beside you at the start, and all its neon siblings belong to Dallol. And Dallol holds a record that is genuinely difficult to sit with when you're used to a temperate life. It is not simply that the afternoons get hot. It is that the average temperature, worked out across an entire span of years, measured carefully between 1960 and 1966, day and night, cool season and hot, summer and the thing that passes for winter here, comes out at around 34.5 degrees Celsius, 94 degrees Fahrenheit, as an average, for the whole year, every year. Let that number find its true weight. Most of us think of 34 degrees as the temperature of a fierce heat wave, the kind of day the news warns you about, the kind of day you close the curtains against and move slowly and drink more water than you want to. A day you endure and then feel relieved when the evening finally cools it off. Now take that single dreaded day and stretch it across the calendar. Make it the ordinary. Make it the baseline that the truly hot days climb up from. Because that 34 is only the average, remember, the middle of the seesaw. The actual daytime highs here climb up toward 45 and 50 degrees Celsius, well past 120 Fahrenheit. The sort of heat that presses on your chest like a hand, that shimmers the horizon into liquid, that makes the very air feel like something you have to push through rather than breathe. This is the hottest inhabited place on Earth, measured by that long yearly average. Not the hottest afternoon ever recorded somewhere for an hour. The hottest place, all the time, where human beings still somehow make a life, and there is almost no water falling from that brass sky to soften any of it. Rain here is a rumour. In a whole year, this basin might receive less than 200 millimetres of rainfall, and to make sense of that, picture a ruler standing up on its end. 200 millimetres is only about the length of your outstretched hand, from wrist to fingertips, and that is the entire year's rain, if it even manages that much, and usually it manages far less. And what little does fall barely gets the chance to land. The heat is so absolute that raindrops evaporate almost as they arrive, lifting back off the ground as ghost steam before they can gather into anything. Hyperarid, the scientists call it, beyond arid, beyond merely dry. Dry in a way that has forgotten what wet even means. A place where the sky keeps nearly all of its water and the land is left to crack and glitter under the weight of the sun. So already you can feel the shape of it forming under you in the dark. A bowl pressed low into the continent, over 100 meters beneath the distant sea. The hottest lived-in place on the planet. Almost no rain, and what comes evaporates before it settles. And down at the bottom of that bowl, those pools, boiling, saltier than any ocean, acid past the edge of the scale, glowing their impossible greens and yellows. It sounds, put like that, like a place with no purpose except to be terrible. A place you would name in an old story and warn your children away from. But a bowl like this does not press itself into a continent by accident. Something is pulling it down. Something enormous and slow and utterly patient is at work beneath the salt, and it has been at work for millions of years. And it is the reason for every strange thing we will meet tonight: the heat, the acid, the glowing water, and the ocean that is coming. So let me tell you softly what is happening underneath. The skin of the earth is not one solid shell. It is broken into great slabs, enormous, rigid plates of rock that fit together across the whole globe like the cracked pieces of an eggshell, or like the sections of a paved courtyard that has slowly, over ages, begun to shift. These plates are not still. They drift. Not fast, nothing here is fast, but they drift, carried on the hot, slow churning rock beneath them, and along the seams where they meet, the great events of our planet happen. Mountains rise where they collide, and where they pull apart, the ground splits and sinks and opens. The Danakil Depression sits over one of the most remarkable seams anywhere on Earth. It has a name that sounds almost gentle, the Afar Triple Junction. But hold that word triple, because it is doing an extraordinary amount of work. Most seams on the planet are a meeting of two plates, two pieces of eggshell grinding past or pulling away from each other, one boundary, one line. Here there are three. This is the only place on dry land in the entire world where three of these great rift systems come together and meet at a single point, three separate tiers in the crust converging on one battered patch of desert. Picture it like this. Slowly, imagine an old floorboard or a stretched sheet, and imagine three long cracks running out from a single spot in three different directions, like the spokes of a wheel with one spoke missing, or the way a pane of glass fractures around the place a stone struck it. Along one of those cracks lies what geologists call the Red Sea Rift, along the second, the Gulf of Aden Rift, and along the third, running deep down into the continent, the East African Rift. The enormous, famous tear that is slowly, gradually working to split the whole eastern edge of Africa away from the rest. Three rifts. One meeting place. And that meeting place is here, beneath your feet, beneath the salt and the glowing pools. And the three plates those rifts belong to are drawing apart. There is the Nubian plate, the great slab that carries most of the African continent. There is the Somalian plate, on the other side, carrying the eastern horn of Africa. And there is the Arabian plate to the north, the one that bears Arabia. Three plates meeting at this triple junction, and all three of them are pulling away from one another, easing open, widening the seam, year after year after year. That is why the bowl is a bowl. The ground is not just sitting here, it is being stretched thin, like dough pulled from three sides at once, and as it stretches it sags and drops, sinking lower and lower into that deep depression, opening the floor to all the heat rising from below. This is the engine. This is the reason for everything. The heat that makes it the hottest inhabited place on Earth comes rising up through crust that has been stretched thin and weak. The boiling, acid, mineral-loaded water in those neon pools comes from that same restless heat below, driven up through cracks and fissures that a stable, quiet piece of continent would never have. The whole harsh character of the Danakil is written by these three plates and their slow, unstoppable parting. The place is extreme because it is a place caught in the very act of tearing open. And I promised you we would come back to the sea, so let me plant that seed properly now, and then let it rest until later. When three plates pull apart like this, and the land between them keeps sinking, there is really only one destination this story can have. The bowl gets lower, the seam gets wider. And one day, not in your lifetime, not in 1,000 lifetimes, but one day, on the vast unhurried clock that the earth keeps, the barriers that hold the ocean out will fail, and the water will come in, and this desert will become a seabed. A new ocean will be born right here, in the lowest, hottest, driest place we know. The Horn of Africa will be carried away on its own plate like a raft cut loose. It is already beginning. There is even fresh crust, new rock of the kind that floors the deep oceans, quietly forming beneath the depression as we speak. You are lying beside the cradle of a sea that does not yet exist. But that is a later chapter. Let it drift for now. And there is a second seed I want to plant, just as gently, because it is the other end of the same astonishing thread. This deadliest of deserts, this bowl of salt and acid and unbearable heat, this ground that seems to refuse life so completely, this same region, this same Afar, is one of the places where we found our own beginnings, where the oldest bones of the human family were lifted out of the sediment. The place that looks most like a dead end on the surface holds, buried in its layers, some of the deepest evidence of where we came from. But that too is for later. I only want you to know it's there, waiting at the far edge of the night, so that as we move through the heat and the chemistry, it can hum quietly underneath. A promise that this desolation has a secret tenderness folded inside it. For now, come back with me to the surface, to the rim of that boiling green pool, because I want you to really understand what you are looking at and why it matters so much to the people who come here in their sun-bleached gear with their instruments and their sample vials. They do not come for beauty, though it is beautiful in its terrible way. They come because this place does something almost nowhere else on Earth can do. It piles the hardships up. In most difficult environments, life faces one great challenge. In the deep sea, it is crushing pressure and cold and dark. In a hot spring, it is heat. In a salt flat, it is salt. And life, clever and patient, has usually found some way to master a single challenge, one at a time, evolving its quiet tricks to endure the one thing that place throws at it. But here, in these pools, the challenges do not come one at a time. They come all at once, stacked one on top of another, each one alone already near the limit of what living tissue can bear. The heat alone would be a wall. The salt alone would be a wall. The acid alone, acid past the bottom of the scale, would be a wall. And this water hands you all three walls in the same cupful at the same instant. To live here, you would not need to be tough in one way. You would need to be tough in every way simultaneously, and being tough against heat often makes you fragile against salt. And the defenses against acid can leave you defenseless against the heat. The stresses fight each other inside anything that tries to endure them. And that is precisely why scientists prize this spot. If you want to find the true edge of life, the real, final boundary, not some soft approximation, you have to find a place that pushes on every side at once and see what, if anything, is left standing when all the pushing is done. That is the question we opened with, and now you can feel why it is the right one. Not the comfortable "how does life survive here?" The sharper, colder, more honest question. Where does life finally give up? And Danakil, this stretched and sinking bowl over the only three-way seam on land, this hottest of inhabited places, under its rainless brass sky. Danakil is one of the few addresses on the whole planet where that question can actually be put to the test. Where you can walk right up to the edge and look over it. And when scientists did walk up to that edge and dipped their instruments into those glowing pools and carried the water back to their labs, they did not all come home agreeing. Some of them found, clinging to the mineral chimneys, the faintest ghost of life, tiny, tiny things, barely more than a rumour of a cell, hanging on where you would swear nothing could. And others looked at the very same hottest, saltiest, most acid pools and concluded, carefully, with evidence, that here at last was water that was truly and completely dead. Not difficult for life. Not challenging for life. Forbidden to it. Sterile. A liquid that looks like water, pours like water, steams like water, and yet slams every door against living things so firmly that nothing, no matter how stubborn, can ever move in. Two teams. The same springs, opposite answers. And the argument between them is not a failure of science, it is science doing exactly what it should, feeling along a boundary so fine and so strange that reasonable people looking at the same neon water can honestly disagree about which side of the line it falls on. That disagreement is where we are heading tonight, slowly, in no rush at all. It is the real treasure buried in this desert, more surprising than any colour, more valuable than any record temperature. But before we can stand between those two teams and understand why they part ways, you have to understand the water itself. Truly understand it, not just be told it is nasty. You have to know why it glows, where the salt came from, what fills the air above it, why one nearby pond kills any bird foolish enough to land on it, and how a place this hostile can be, at the same time, the closest thing on our own planet to the surface of another world. That is the ground we'll cover as the night goes on, one gentle step at a time. So stay low with me, here at the rim of the bowl, for a little longer. Feel the strange facts settle into place beneath you, like stones sinking softly into silt. A depression pressed 116 meters below the sea. The hottest lived in place on the planet, 34.5 degrees as its patient yearly average, climbing toward 50 in the blaze of the afternoon. Rain that evaporates before it lands, in a basin that has all but forgotten water even as it drowns in the wrong kind of it. 3 great plates, Nubian, Somalian, Arabian, easing apart along 3 rifts that meet, alone in all the world, right here. And down at the bottom, those pools, boiling and saltier than the sea, and acid past the edge of the scale, glowing greens and yellows that no living thing painted, and the quiet, patient question hanging over all of it, the question we will follow like a thread to the very end. Not whether life is a miracle that always finds a way in, but where, exactly, in a place built to break every rule at once, life finally runs out of room. Where it gives up, where the last door closes. Let that question rest on you now, weightless, the way a question does when you're almost asleep and no longer trying to answer it, just holding it, turning it over slowly in the warm dark. There is no need to solve anything tonight. The pools will still be glowing when we return to them. The plates will still be parting, a slow centimetre at a time. And the answer, or the honest lack of one, will still be waiting out there under the brass-coloured sky. For now, we have only just arrived at the rim. We have felt how low the ground has sunk, and how hot the air has grown, and how the whole basin is being pulled open by forces older and larger than anything a single human life can hold. We have not yet climbed down among the salt terraces. We have not yet learned why the water wears its impossible colours, or where all that salt came from in a place with no sea. We have not yet met the pond that kills, or the mountain nearby that has held a lake of living fire for over 100 years, or the scientists standing at the boundary with their vials and their disagreement. That is all ahead of us, and there is so much night left, and nowhere at all that we need to be. So, the salt. Start with the salt, because everything else, the colours, the chemistry, the reason scientists pack their vials and fly to this corner of northeastern Ethiopia at all, everything else is downstream of it. And the salt has a story that is almost impossible to hold in the mind all at once, because it asks you to imagine time on a scale that makes a human lifetime feel like a single breath in a very long sentence. Picture the basin as it sits now. The floor of it, out near Lake Asale and Lake Karum, where the ground sinks to its lowest, lies roughly 116 meters below the level of the sea. Below sea level, right now, tonight, under the open sky. And what fills that floor, what has been accumulating there for hundreds of thousands of years, layer pressed on layer, kilometre upon compressed kilometre, is salt. Evaporite deposits, crystals of halite and potash and gypsum and other minerals with long names, all of them left behind by water that came and then left and then came again, in cycles longer than our entire species has existed. Here is what happened in the simplest version of a very complicated story. The Afar Basin was sinking, It is still sinking, slowly, pulled downward by the same forces that are pulling the plates apart. And as it sank, there were intervals, long intervals, spanning tens of thousands of years at a stretch, when the Red Sea would breach the low edge of the land and pour in. Not dramatically, not all at once the way a dam breaks. Gradually, the way a tub fills when you leave the tap barely open. Water working its way through the lowest available gap, spreading across the floor of the depression, pooling in the heat. And then the heat would take it back. In a place with almost no rainfall, the basin receives well under 200 millimeters a year, and even that thin blessing evaporates almost before it lands. The sun and the dry air are relentless accountants. Every drop of water the Red Sea sent in, the atmosphere eventually claimed. But water evaporates clean. It leaves everything it carried behind. Minerals, salts dissolved from rock and seafloor, concentrated over time into brine and then into crust. The sea would retreat or evaporate, and the basin would be left with a new layer of salt on top of the last one. Then the sea might flood in again thousands of years later, and the process would repeat. Do it enough times, over enough hundreds of thousands of years, and you get what sits beneath the Danakil floor today, salt deposits kilometres thick in places. A record, laid down in layers like the pages of a book you could read from bottom to top if you could drill down far enough. Of every ancient inundation, every long evaporation, every cycle of flood and dry and flood again. Think of it like a candle that someone dipped over and over in wax. Each pass adds a thin new coat, and over years the candle grows thick and strange, all the old layers preserved inside. The Danakil salt is that same idea, except the candle is a continental basin, and the wax is an ancient inland sea, and the years are measured in spans that make recorded history look like the last fraction of a millimetre on the outermost layer. The Afar people who live here and have lived here longer than any written account can reach, they know this salt in a direct, tactile, everyday way. They cut it. With picks and flat blades, working in teams under a sun that can push daytime temperatures to 45, 50 degrees Celsius, they score the surface of the salt flats into rectangles and lever the blocks free. Each block, called an amole, is a standard size, flat-sided, dense, the weight of something you would carry in both arms. Camels carry them out, long trains of them winding across the flats and up the edge of the basin toward the highlands. Those blocks of salt, those amole, were for a very long time not merely a commodity. They were money. In the Ethiopian highlands, where the Danakil's impossible surplus met the cooler, greener world of the interior, salt bars functioned as currency. You traded them. You paid debts with them. The value of a camel or a sack of grain could be expressed in amole. The ground of one of the harshest places on earth was, in a sense, a mint. And the Afar miners were its workers, doing in the heat what generations before them had done, cutting wealth from a floor that was itself made of an ancient sea. The salt caravans still move. Still today, centuries of practice in the same motion, pick, lever, stack, load, walk. The route from the salt flats to the highlands is a journey that would exhaust most people in the first hour, and the Afar have been making it so long it has shaped the posture of their lives. But understanding why the salt is there, why the floods came and evaporated and came again, only tells half the story of what made this basin what it is. The other half lives deeper down, far beneath the salt and beneath the sediments, and beneath even the older rock, in a place that is genuinely hard to picture because nothing in ordinary experience gives you a good frame for it. There is a column of unusually hot mantle rock rising beneath the Afar. Geophysicists call it the Afar mantle plume, or the Afar hotspot. Think of it as a blowtorch aimed upward from deep inside the earth. Or if that's too violent a comparison, think of it as a place where the mantle, which is not liquid the way water is liquid, but hot and slow and capable of flowing over geological time, wells up hotter than the surrounding rock, pushing toward the surface like a bubble in very thick oil. That rising plume does several things at once. It adds heat to the crust from below, making it thinner and weaker and more susceptible to the pulling apart that the three diverging plates are doing from the sides. It drives the volcanism you can see at the surface. It is, in a real sense, the engine under everything. The reason the Afar region is what it is, rather than just another stretch of dry highland. Without the plume, the plates might still be separating, but far more slowly, far more quietly, without the volcanic intensity that has made this basin so chemically extreme. And it is that volcanic intensity, funneled through the specific geology of the Dallol area, that produces what the photographs always capture: the colours, the towers, the impossible greens and yellows, even though the photographs almost never explain where any of it actually comes from. Dallol is not a mountain, at least not in any sense you would recognize from a distance. It is a low, sprawling hydrothermal field, the product of what geologists call a phreatic eruption, which is worth pausing on because the word sounds technical, but the idea is vivid once you have it. A phreatic eruption is a steam explosion. Not lava, not ash thrown from a magma chamber. Water, groundwater or seawater that has seeped down through cracks in the rock, meets intensely hot material underground, flashes to steam, and the pressure blows a hole. Violently, rapidly, it happened at Dallol in 1926. The crater that eruption left sits now several tens of meters below sea level, which puts it lower than almost anything around it, and it has been quietly expressing its hydrothermal energy ever since. Hydrothermal means heat plus water moving through rock. Rainwater and briny water from the surrounding salt flats seep down. They pick up heat from the volcanic system below. They dissolve minerals from the rock they travel through: iron compounds, sulfur compounds, potassium and other salts. And then they rise again, forced back to the surface by pressure, emerging through vents and cracks in the crater floor, as springs, as pools, as the bubbling. Hissing, visually extraordinary features that have made Dallol famous. The colours come from those dissolved minerals meeting air and daylight when they reach the surface. Iron, when it oxidizes, when it combines with oxygen in the same basic process that turns a nail left in the rain to rust, produces a range of colours from yellow to orange to deep red. The specific iron hydroxides and oxides that precipitate out of Dallol's springs create the ochre and orange tones. Sulfur, pure elemental sulfur deposited from the sulfur-laden fluids, is a vivid egg yellow, so intensely yellow it looks almost artificial, almost like someone applied it with a brush. Potassium salts contribute their own whites and pale yellows. Other dissolved minerals add to the palette in smaller ways. None of these colours come from life. There are no vast mats of algae, no microbial films painting the terraces the way cyanobacteria colour the hot springs at Yellowstone in the United States. Or at least, and this is where the story gets genuinely complicated and where we will need to spend more time later, not in the hottest, most chemically extreme areas. For now, understand this: the neon display is a chemical one. mineral precipitation from water that has traveled through a volcanic system and emerged carrying its dissolved cargo to the surface. And the structures, the salt chimneys, the terraces, the small towers and irregular formations that look, there is really no other word for it, alien. Like something a geologist from another planet might sketch if you asked them to draw what a world without life might look like. Those structures are actively growing. This is one of the genuinely strange and wonderful things about Dallol. It is not a static ruin or a preserved ancient formation. The hydrothermal fluid rises through layers of salt and mineral crust, and as it reaches the surface and cools slightly and meets the dry air, it deposits new material, crystals and precipitates, building on what is already there, adding to the chimneys and terraces month by month, year by year. The landscape is changing. A chimney that existed 10 years ago may have grown taller or been dissolved or toppled by a new vent opening nearby. The pools shift. The colours rearrange. The whole field is a slow, ongoing process of formation rather than a finished thing. Imagine a coral reef in very slow motion, except the builder is not a living animal, but a solution of minerals in hot acidic water. And the reef is made of salt and iron and sulfur instead of calcium carbonate. That sense of a growing, accumulating, actively constructing system. That is Dallol. But the air above it, the air you would be breathing if you were standing at the edge of one of those pools. This is the part the photographs cannot convey, and the part that makes any extended time at Dallol a genuine risk rather than just a visual experience. The venting fluids carry gases. Hydrogen sulfide is the one most people have encountered in small amounts without knowing it. It is the gas responsible for the smell of rotten eggs, and even at concentrations too low to see or taste it distinctly, it is toxic. At the concentrations present near active vents, it is acutely dangerous. There is also sulfur dioxide, which has a sharp, choking quality that you feel in the throat before you understand what is happening. And chlorine-bearing vapours, generated by the acidic chemistry of the brines, add their own corrosive contribution to the mixture. Researchers who work at Dallol do not linger. They move in teams, they carry monitoring equipment. They watch the wind direction, because the difference between standing upwind of a vent and downwind of it is the difference between a research day and a medical emergency. The Afar salt miners know the field too, and they know its moods. They know which areas to skirt and which days the gases are stronger and when the wind is wrong. This knowledge is not written down anywhere. It is carried in the body, passed through experience, a kind of chemical literacy built over generations. If you were there now, hypothetically, standing at the rim of the crater in the deep of the night, what you would notice first is probably not the smell, though it would be there, low and sulphurous, at the edge of perception. You would notice the silence, and then the sound inside the silence, a faint hissing from the nearest vents, the occasional bubble releasing from one of the pools, the settling creak of salt cooling in the darkness. The colours, which in daylight are almost aggressively vivid, would be muted now, the yellows gone grey, and the greens reduced to something between black and the darkest imaginable teal. The shapes would still be there, the chimneys, the terraces, the irregular rims of the pools, visible as silhouettes against a sky deep with stars. The stars, out here, with no city light for a very long distance in any direction, the sky is not the way most people now ever see a sky. The Milky Way is not a suggestion or a smear, it is a structure. You can see its banding, its clouds and gaps, the way it thickens toward the galactic center. There are more stars than black, which is an arrangement of sky that surprises people who have only ever looked up from a lit city and forgotten this is what night originally meant. 90 kilometers away from where you are standing, give or take, close enough on a geological map that your finger covers both at once, far enough on foot that it would take days, is something that deserves its own particular pause in this story. Erta Ale is a shield volcano, broad and low-shouldered, rising to just over 600 meters above the surrounding plain. Its name in the Afar language means smoking mountain, and it has been living up to that name persistently since at least the early years of the 20th century, when the first external records of it were made. What it has in its summit caldera, and has had, continuously or near continuously, for over 100 years, is one of the rarest things on Earth. A lava lake, not a lava flow, not an eruption that opens a channel of molten rock and then subsides. A lake, a body of liquid basalt held in a bowl at the volcano's top, circulating, surfacing, cooling slightly at the edges, and then being stirred under again by convection, always renewing, always present. There are very few of these on Earth. You could count the persistent ones on the fingers of one hand, with fingers left over. And Erta Ale has maintained its for longer than most people alive today have been alive. At night, from a certain distance and angle, the glow is visible, a pulsing orange light against the underside of any smoke or steam rising from the caldera, painting the sky above the volcano a faint and unsettling bronze. Not constant, not regular, just there, and then more there, and then less, the way a fire breathes. 100 and some years of that same light through all the human events of the 20th century and into the 21st. While the lake circulated and cooled at its edges and bubbled at its center, entirely indifferent. If you have ever stood at the edge of a campfire and felt the specific quality of attention that an open flame demands, the way you watch it without quite deciding to, the way it holds you, multiply that by every dimension. Make the fire a lake, put it inside a volcano, let it be 100 years old and still going. That is Erta Ale on a clear night. It is part of the same system. The same mantle plume, the same rift tectonics, the same volcanic energy that drives the hydrothermal springs at Dallol also drives the persistent lava lake at Erta Ale. They are expressions of the same deep process, spaced 90 kilometers apart, like two windows into the same interior. Now come back from Erta Ale, come back across the dark plain, across the salt flats, to something much smaller and much closer to the crater field at Dallol. Gaet'ale Pond. It does not look like much from a description. A pool. Roughly circular, not large, its surface with an oily, iridescent quality in strong light and a persistent release of gas bubbles rising from somewhere below. What makes it remarkable, what earned it the reputation behind the Afar name that translates, loosely, to something like the spring that killed the goat, is its chemistry. The salinity of Gaet'ale has been measured at around 43%. 43% dissolved salts by weight. To give that number some scale, seawater, normal open ocean seawater, runs at roughly 3.5%. The Dead Sea, famous for the way a person floats in it without effort, famous for being so salty that almost nothing lives in it, sits somewhere around 30 to 34% in its saltiest parts. Gaet'ale is saltier than the Dead Sea, saltier by a margin that makes the Dead Sea seem almost drinkable by comparison. Nothing swims in Gaet'ale, nothing grows on its surface, birds that land on it, drawn perhaps by the glimmer that water makes. The visual signal of moisture in an otherwise dry and dusty landscape do not take off again. The surface tension that should let a bird push off is gone, replaced by the dense, viscous grip of an almost saturated brine. Insects that land on it are lost. The pond is not venomous in any dramatic sense. It does not reach out or strike. It simply holds what comes to it. Still, impassive, lethal by total indifference to anything that requires fresh water to function, which is to say lethal to nearly everything we would recognize as alive. Gaet'ale grew. That is another strange detail. Following seismic activity around 2005, the pond expanded, an indication that the underground plumbing connecting it to the hydrothermal system shifted, altering the balance of inflow and concentration. A landscape that already seemed static, salt and stone and silence, rearranged itself in response to the slow violence happening beneath. The pond does not sit unchanged. Nothing here does. The gas that bubbles up from Gaet'ale adds to its texture. Carbon dioxide, most likely, rising from the same deep volcanic system that drives everything else in this basin, seeping up through the brine and breaking the surface in lazy clusters of small bubbles that suggest, almost comically, a glass of extremely dense and entirely undrinkable mineral water. The oily film on the surface, which can look, in certain light, almost beautiful, with the shimmering iridescence you see in a puddle with a trace of engine oil, is a product of the mineral-rich fluid interacting with the surface layer and the gas release. Beauty and lethality wearing the same coat. And yet people come here. Not just researchers, not just the Afar who live in this landscape and know it the way you know the inside of your own home, but also the salt miners, the camel herders, the occasional traveller who has made the difficult journey in from the nearest road. They come and they look at the pond and they step back from its edge, and they understand, without needing a sign or a warning, that this is not water in any sense that is friendly to them. The Afar knowledge of this landscape is deep and practical and old in a way that no expedition or study has quite managed to replicate. They know which directions to walk when the gases are rising. They know which pools are which season and which wind condition changes their character. They know the salt flats and their surfaces, which sections hold weight and which have thin crusts over softer brine beneath, the kind of surface that swallows a foot. They know the route from the flats up the escarpment and down again, in heat that would incapacitate a person without that knowledge within a few hours. The camel caravans that carry the Amole salt blocks out of the basin follow routes that generations of people worked out through experience and cost. The salt mining itself is timed, early morning, before the worst of the heat, with breaks calculated not by a clock, but by the body, by how much a person can do before needing water and shade. The work is communal. Teams cut and a team stacks, and the camels are loaded by people who know how to balance the weight so the animal carries it for the distance required. Each Amole block, cut, flat-sided, dense, represents a decision about dimensions that was worked out long ago. Not too heavy to carry, not too light to be worth the trip, consistent enough in size to function as a standard unit of exchange. Because that is what it was, salt as money. In the highland markets of Ethiopia above the rim of the basin, where farmers and traders gathered, the Amole was recognized and accepted. You did not need a bank or a mint or an authority to validate it. You needed only the salt itself, which everyone needed and which only certain places could produce. And one of those places was this basin with its ancient seed of crystallized minerals. Think about the chain of that. Deep underground, a column of unusually hot mantle rock. Above it, 3 tectonic plates pulling apart at the rate your fingernail grows. Above that, a sinking basin that collected the overflow of an ancient sea and concentrated it under a sun that evaporates almost everything it touches. And from that compressed geology, from millions of years of submersion and evaporation, comes a material that people carry by camel to a market and use to buy grain. The connection from mantle plume to salt bar to trade is not a metaphor. It is a physical chain, and every link of it is real. There is something that settles in you when you follow that chain all the way through. Not awe exactly, or not only awe, but something quieter. A sense of how much has to go right, how many unrelated things have to align for a single ordinary transaction to be possible. A farmer hands over a goat, a miner hands over a stack of salt bars. Both of them are, without knowing it, standing at the end of a geological and chemical process that began before any human being existed. The salt flats where the mining happens, the area around Lake Asale and Lake Karum, have a particular quality at the right time of day. Early morning, before the sun has climbed high enough to turn the light harsh. The flat white surface of the salt gives everything above it a clean, luminous quality, like a room with white walls that catches all available light and distributes it evenly. The mountains of the escarpment to the west are visible in that light with unusual clarity, their ridges sharp. The camels moving across the flats cast long shadows. The blocks of salt glow faintly. And below all of that, below the miners and the camels and the blocks and the flats and the ancient crystallized sea, the Afar mantle plume continues its slow, immense, entirely unconscious work, pushing heat upward, thinning the crust from below, adding its contribution to the rifting that the plates are doing from the sides. The system does not know about the miners. The system does not know about the amole blocks, or the markets, or the goats, or the grain. The system is just doing what physics does when rock is hot enough and pressure is distributed in a particular way over a particular span of time. It built this place without intending to build anything. And into the place it built, life came. And with life came salt miners and camel routes and currency and trade. And into those same extreme pools and springs, much more recently, came scientists with a very different set of questions, not about trade or economics or human survival, but about the deepest possible version of the question: what is living and what is not? And where is the line between them? That line is what we will follow next, down among the acid springs and the mineral towers and the neon-lit terraces of Dallol, where 2 teams of researchers arrived in 2019 with the same equipment, looked at the same landscape, and came back with answers that directly contradict each other. But not yet, not quite yet. For now, let the basin sit around you in the slow dark. The salt flats with their faint luminescence, the acid springs cooling toward whatever night temperature they reach, the chimneys still growing by fractions of a millimetre in the dark, the minerals still precipitating, still adding to the terraces, the gas still venting from the nearest cracks, a thin sulphurous thread in the still air. Gaet'ale still holding the surface of its oily, undrinkable brine, its gas bubbles still rising, its density still absolute. Erta Ale still glowing, 90 kilometres away, the lava lake circulating in its caldera as it has done for longer than any living person can remember, as it will likely continue to do long after any living person forgets this night, or this voice, or this journey through the dark. The salt caravans are resting. The camels have been unloaded and settled for the night somewhere up on the cooler edge of the basin, where the air is less heavy, where the gases do not reach. The Afar miners are sleeping the way people sleep when they have done genuinely hard physical work in genuinely hostile heat, completely, efficiently, without the restlessness of people who have too many options and not enough exhaustion. And the mantle plume goes on doing its work as it has for millions of years, unwitnessed and unremarked and utterly indifferent to whether anyone is watching, pushing heat up through rock that is slowly thinning, feeding the volcanic system that drives the springs and the gases and the towers, setting the conditions for what scientists, when they arrive with their instruments and their arguments, will call one of the most Mars-like environments on Earth. That is the next thought to fall asleep on, if you have not already gone. Not the danger, or the heat, or the impossible salinity of a pond that kills by density alone, but the stillness of it. The way an extreme place, in the dark, when the temperature drops a few degrees, and the human visitors are gone, and the work has stopped, is simply a landscape. The way it does not announce its extremity. The acid pools do not smell more acidic at night. The chimneys do not glow with their own light. The mantle plume does not signal its presence in any way you could see from the surface. It is simply there, old beyond any frame a single life can provide, patient in the way only geology can be patient, which is to say not patient at all in any emotional sense, but just unchanged on timescales we cannot feel. Let that be enough for now. The salt below you, and the stars above you, and the warm dark of the basin all around. The mantle plume below the salt. The acid springs somewhere off to your right, their chemistry doing what chemistry does without requiring your attention. The lava lake to the north, breathing its orange light against the night sky. Sleep, if you can. The scientists and their disagreement will still be here when you wake. And they do come, the scientists. They have been coming for years now, arriving in convoys of four-wheel drive vehicles with satellite phones and gas monitors clipped to their shirt collars, carrying equipment cases sealed against the dust and the humidity and the sulphurous air that is thick enough on a still morning near the hydrothermal field, to make your eyes water before you have even stepped out of the vehicle. They come from Bologna and Madrid and Paris. They come from universities with long names and from research centres whose acronyms you would not recognise unless you moved in those particular circles. They set up sampling stations near pools that smell like the inside of a struck match, and they collect water in sealed vials. And they argue about what the numbers mean. What draws them here is not the spectacle, though the spectacle is undeniable, those neon terraces and the mineral chimneys and the colours that have no business existing in a desert. What draws them is something quieter than spectacle. Something that begins not with beauty, but with a question, and the question is this: where, exactly, does life stop? Not where does life struggle, not where does life slow down or thin out or become rare. Where does it actually, truly, finally stop? Where is the line, if there is a line, on the other side of which no organism, no microbe, no spore, no fragment of biology clinging to a crystal surface can persist? That question has haunted biology for as long as biology has been a discipline. But for most of that time it was academic, in the original sense of the word, a puzzle of philosophy rather than urgency. Then something changed. We started pointing telescopes at other worlds and sending machines to crawl across them, and we found things. We found iron, we found sulfur, we found ancient riverbeds on a planet where no river runs today. And we found the chemical ghost of acidic water pooled in basins that have been dry for 1 billion years. We found, in other words, that the universe does not confine its chemistry to the comfortable middle range. Other worlds are extreme. And so the question of where life stops on Earth stopped being academic and became a matter of genuine planetary importance. That is why they come to Dallol. If you had stood on Mars some 4 billion years ago, in the region scientists now call Meridiani Planum, the ground beneath your feet would have looked nothing like the dry red desert it looks like today. It would have been wet, not lush, not temperate, not anything a person could have walked through comfortably, but wet in the chemical sense, saturated with a particular kind of chemistry that leaves traces even after the water is long gone. The rocks at Meridiani, the ones NASA's Opportunity rover spent years crawling across, are laden with hematite, iron oxide, in a form that, on Earth, forms almost exclusively in the presence of water. Small spheres of it embedded in the rock, so uniform in size and shape that the science team gave them a nickname, blueberries, they called them. Though they are not blue and certainly not sweet. They are the fossilized signature of water that was there and then was not. The same rocks carry sulfates, jarosite specifically, which is an iron sulfate mineral that forms when sulfuric acid-bearing water sits in contact with iron-rich rock and then evaporates or dries. Jarosite does not form in neutral water, it does not form in clean water, it forms in acid, and the fact of its presence in the Meridiani layered rocks told geologists something important. The ancient water on Mars was not gentle. It was sulfurous and acidic and mineral-rich, the kind of water that would strip paint if there had been paint, which there was not. The kind of water that leaves a very specific chemical signature behind in the rock, a signature as legible as a fingerprint. Dallol's springs leave the same fingerprint. Let that sit for a moment. Not the drama of it, not the science fiction feeling of standing in a place that mirrors another world, but the quiet specificity. When a researcher fills a vial at the edge of a Dallol pool and sends it to a laboratory for analysis, the mineral sweet that comes back, the iron, the sulfate compounds, the hypersilin brine, the particular way the acid has interacted with the basaltic rock below reads like a translation of what Opportunity's instruments were reading on Meridiani Planum. Not identical, because Dallol is Dallol and Mars is Mars, and no analogy is exact. But close enough, specific enough, that astrobiologists use the word analog with a seriousness they reserve for things that genuinely match. There is another dimension to the comparison, one that reaches beyond the surface of Mars to something wetter and colder and farther away. Europa is one of Jupiter's moons, roughly the size of our own moon, and beneath its surface, beneath a shell of ice that may be dozens of kilometres thick in some places, there is almost certainly a liquid ocean. The ice shell is cracked, fractured by the tidal forces Jupiter exerts as Europa orbits, and where those cracks reach the surface they reveal reddish-brown material that has been studied with spectroscopic instruments and found to contain, among other compounds, salts, magnesium sulfate, sodium chloride possibly, the chemistry of a briny ocean that has been in contact with a rocky seafloor for a very long time, exchanging minerals the way oceans do, building up a chemical signature in the water that gets expressed on the surface when that water erupts through the ice and freezes there. Enceladus, which orbits Saturn, does this even more directly. It actively vents plumes of water and ice particles from its southern pole, and those plumes have been sampled by the Cassini spacecraft, which flew through them repeatedly. What Cassini found, water vapor, ice, sodium chloride, carbon dioxide, methane, hydrogen, a hint, some researchers argued, of hydrothermal activity on the ocean floor. Hot water interacting with rock in the dark beneath all that ice. Exactly the kind of environment in miniature that you can find stretched across the Danakil Depression in roughly life-sized form. This is what gives the basin its second identity. Not the one the travel writers reach for, not the gateway to hell label that was always more poetry than description, but a more precise and stranger identity, a working model. A place where Earth's geology, through an improbable combination of circumstances, has assembled the chemistry that exists elsewhere in the solar system, and assembled it in a form that scientists can walk up to and sample and argue over. The benefit of that arrangement is enormous. You cannot send a field team to Meridiani. You cannot walk along Europa's cracked ice and fill vials from the brine below. You can, with the right permits and the right equipment and the right tolerance for hydrogen sulfide in the morning air, drive to Dallol and do those things there. The scientists who arrive with their gas monitors and their sealed sample cases are not merely studying Dallol. They are using Dallol to study elsewhere. They are asking the rocks and the water a question whose answer, if they can find it, applies to every iron-acid, sulfate environment in the solar system and probably beyond. The question is still, where does life stop? But now it carries a weight it did not have before. Because if the answer is that life stops before Dallol's conditions are reached, then every other environment in the solar system that mirrors those conditions is also, by extension, probably lifeless. And if the answer is that something survives even in Dallol's most extreme corners, then the universe of possibly inhabited places expands. The answer, as it turns out, is not clean. And that is where things get interesting enough to keep you awake, if you are still listening, or interesting enough to follow you gently into sleep as the ideas settle and slow. Here is what we know about life and extremity, told in the simplest possible terms. Life, as we understand it, requires certain things. Liquid water is the most fundamental of them, or at least it has been since the beginning of every biology textbook ever written, because water is the medium in which chemistry happens inside cells. Every metabolic reaction, every synthesis of protein, every copying of genetic material happens in solution, and the solution is water. Take away the water and the chemistry stops. The cell desiccates and dies, or enters a state of suspended non-living and waits, but the active life of it is over until the water returns. This is why the discovery of liquid water anywhere in the solar system is treated as significant news. Not because water alone means life, but because life without water, as far as we know, is not really life at all. It is a seed waiting. And so every briny ocean under Europa's ice, every seasonal trickle inferred from slope features on Mars, every plume from Enceladus, is greeted with a particular kind of attention, careful and calibrated, and always hedged with the acknowledgement that water is necessary but not sufficient. The organisms that have figured out how to live in conditions that would kill everything else are called extremophiles. The word means, simply, lovers of the extreme. It is a category designation, not a compliment. The various subcategories of extremophiles sort by the particular kind of extremity they have learned to endure. Thermophiles tolerate high heat. Acidophiles prefer acid environments. Halophiles live in salt concentrations that would shrivel most cells like a grape left in the sun. Each of these is a specialization, an evolutionary bet placed on a particular type of hostility, the accumulated result of millions of generations of natural selection, winnowing out everything that could not cope until only the copers remained. But the organisms that survive in places like Dallol are not, most of them, specialists in a single hostility. They are specialists in several hostilities at once. The term for this is polyextremophile, and it is as ungainly as the creatures it describes are remarkable. A polyextremophile is not something that can handle heat, or something that can handle acid, or something that can handle salt. It is something that can handle all three simultaneously, stacked on top of each other, the combined pressure of which would dismantle most biology in a matter of minutes. The heat denatures proteins, the acid disrupts membrane chemistry, the salt draws water out of the cell through osmosis faster than the cell can compensate. Each stress is survivable, with the right adaptations. All three at once is a different problem entirely, and the organisms that have solved it are genuinely extraordinary examples of what evolution can produce when the selection pressure is unrelenting enough for long enough. The mineral chimneys at Dallol, those pale spires that rise from the brine like strange architecture and grow and reshape over months and years, as hydrothermal fluid deposits mineral after mineral on the way to the surface, are the kind of structure where you might expect to find polyextremophiles if they exist here at all. The chimneys are not simply decorative. They are interface zones, places where fluid at one chemistry meets air at another chemistry, where temperature gradients are steepest, where precipitation is happening actively and minerals are locking into new forms. Interfaces are often where biology takes hold when it can, because interfaces are where chemistry is richest and most varied, and biological machinery runs on chemical variety. In 2019, a team of researchers led by Barbara Cavallazzi of the University of Bologna, working in collaboration with the Centro de Astrobiologia in Madrid, a research centre that focuses, as its name suggests, on the biology of the universe rather than just the biology of Earth, collected samples from the mineral chimneys and the surrounding structures at Dallol. They examined those samples at the level of the very small, looking for the signatures of biological presence, and what they reported finding was nanohaloarchaea. Say it slowly, nanohaloarchaea. The word carries its meaning in its parts. Nano, because these organisms are extremely small, far smaller than a typical bacterium. Halo, from the Greek word for salt, because they belong to a group of microorganisms associated with high salt environments. And archaea, because they are not bacteria at all, but members of a different domain of life entirely. One of three domains that modern biology recognizes: bacteria, eukarya, which includes everything from yeast to humans, and archaea, which are superficially similar to bacteria under a microscope but genetically as distant from them as they are from us. Archaea were not recognized as a distinct domain of life until the 1970s, when Carl Woese's work on ribosomal RNA revealed that certain microorganisms living in hot springs and salt flats and other hostile places were so fundamentally different from bacteria in their genetic architecture that they constituted an entirely separate branch of the tree of life. The discovery reorganized our understanding of biology at a foundational level. Before Woese, there were two kingdoms of life: prokaryotes, the simple ones without nuclei, and eukaryotes, the complex ones with nuclei. After Woese, there were three domains, and one of them, the archaea, turned out to be preferentially but not exclusively associated with extreme environments. They are not the only life in extreme places. but they are very often the life that goes deepest into the extremes, that tolerates what nothing else will. The nanohaloarchaea found within Dallol's chimneys, as reported by the Cavalazzi team, were framed in a specific context. Not that Dallol was teeming with life, not that extremophiles were thriving happily in the sulphurous pools. The claim was more careful, that within the mineral structures, in the zones where the most extreme chemistry was slightly buffered by the physical architecture of the chimney itself, where temperature might be a degree or two lower, where mineral precipitation had created microenvironments that differed chemically from the open pool just meters away, there was evidence of microbial presence. Small, constrained, not abundant. But there. The team published their findings in scientific reports. They framed Dallol as a Mars analogue explicitly, noting that the conditions in the chimneys, the combination of extreme salinity, acidity, and heat, paralleled conditions that may have existed on early Mars, in environments where hydrothermal activity drove acidic brines through sulfate-rich rock. The implication was not that Mars had nanohaloarchaea, or that it certainly once had life. The implication was that if life could exist in the mineral chimneys of Dallol under these stacked conditions, then environments on early Mars with comparable chemistry were not automatically sterile by default. They were within the range that life, as we understand life on Earth, might have occupied. This is the careful way science works when it touches astrobiology. Nothing is overclaimed. Nothing is stated as more than what the data show. But the implications, stated or unstated, are enormous and obvious, and they are why the work attracted attention beyond the journals. There is, however, a counterpoint. And the counterpoint is where the real science lives, where the genuinely interesting and genuinely unresolved argument sits, and it is the counterpoint that makes Dallol not simply a place where life clings against the odds, but a place where life runs into something it cannot overcome. To understand the counterpoint, you need to understand something about water that goes beyond the simple fact of its presence or absence. The conventional biological wisdom is that where there is liquid water, there is at least the possibility of life. Water activity is what disrupts that simple picture. Water activity is a measure not of whether water is present, but of how available that water is to participate in chemistry. In a glass of pure water, the activity is essentially 1. Every water molecule is free to interact with anything you dissolve in it. In a very salty solution, many of the water molecules are tied up interacting with the dissolved salt ions, clustered around sodium or chloride or whatever else is in solution, no longer free to participate in the chemistry of a living cell. The water is still there. It is still wet, but its activity, its effective availability for biology, is reduced. Push the concentration of dissolved salts high enough and the water activity drops low enough that cells cannot function. The chemistry inside the cell requires water molecules to be available. Proteins fold in the presence of water, and that folding is not simply a physical process of a chain of amino acids collapsing into the right shape. It is a water-mediated process. The hydrogen bonding and hydrophobic interactions that determine a protein's three-dimensional structure depending entirely on the behavior of surrounding water molecules. Drop the water activity far enough, and proteins do not fold correctly. Membranes cannot assemble properly. The whole machinery of life, which is a machinery of water-mediated chemistry, starts to fail. In an ordinary salt solution, this effect is manageable. Halophiles have evolved mechanisms to cope with reduced water activity, accumulating compatible solutes inside the cell that balance the osmotic pressure outside without disrupting the chemistry inside. They have evolved versions of proteins that function in the presence of high salt concentrations. They are remarkable for having solved this problem, but they have solved it within a range. Push far enough past the upper end of that range, and you are outside what any known biology can handle. Dallol adds a different complication on top of this one, and the complication has a name that deserves to be said clearly. Chaotropicity. A chaotropic substance is one that disrupts the structure of water beyond the simple reduction of water activity. Magnesium chloride, which is abundant in some of Dallol's brines, and calcium chloride, also present, are chaotropic in the relevant sense. They interact with water molecules in a way that physically destabilizes the structured hydrogen bonding network that water normally maintains. And when that network is disrupted, proteins which fold and function within that network are destabilized too. They unfold, they aggregate in the wrong shapes, they stop doing what they are supposed to do. The term for this unfolding, this loss of the three-dimensional structure that makes a protein functional, is denaturation, the same thing that heat does to an egg white. What this means in practice is that magnesium chloride brines can be destructive to biological molecules, even at temperatures where thermophiles could in principle survive, and at salt concentrations that halophiles might otherwise tolerate. The chaotropic effect is an additional, independent chemical attack on the machinery of life, one that operates by a different mechanism than heat or acidity, and one that stacks on top of them in exactly the most hostile combinations. In the most extreme ponds at Dallol, all of these things operate simultaneously. The temperature is boiling, or near enough that the distinction is largely academic for any organism trying to live in it. The pH is near 0 or lower, in pools where the concentration of sulfuric acid is high enough that the conventional pH scale barely applies. The salinity is extreme, and the chaotropic brine, magnesium-rich, calcium-rich, actively destabilizing to water structure and by extension to any protein that tries to exist within it, is present in abundance. These are not individually extreme conditions, each of which has been individually surmounted by some organism somewhere. They are simultaneously extreme conditions, all operating at once, and the question of whether any known organism can survive the combination is genuinely open. This is where you reach the edge. Not a dramatic edge, not a cliff you can stand on and look over. A quiet edge, a chemical edge. The kind you can only find by filling vials and taking them to laboratories and running analysis after analysis until the numbers tell you something. But it is a real edge, and Dallol is where it was found, or at least where it was first argued over seriously enough to make it into the literature. The pools that the Cavallazzi team sampled for their nanohalo archaea finding were not necessarily the most extreme pools. The spatial heterogeneity of Dallol's hydrothermal field means that conditions vary significantly over distances of meters, and some areas that look similar from a distance are chemically quite different close up. A chimney structure buffering the hydrothermal fluid before it reaches the open air has different chemistry from an open pool receiving the same fluid directly. A pool that formed recently after the last small seismic event has different chemistry from a pool that has been sitting and concentrating for months. The field is not uniform, and what is true of one feature is not automatically true of the one 10 meters away. This matters because the 2019 findings from Dallol that made it into the literature were not a single finding, but from two different teams, and they reached conclusions that do not easily reconcile. The Kavalatsi finding of nanohaloarchaea in the mineral chimneys was published in scientific reports. At the same time, a team led by Purificación Elpez-Garca at the CNRs in France was examining Dallol's waters and reaching a different conclusion about the most extreme pools, the hottest, the most magnesium-rich, the ones where the chaotropic chemistry is most pronounced. But that is a story that deserves its own space, its own slow unfolding. The science of disagreement, which is where the real knowledge lives, which is where the boundary of what we know rubs up against the boundary of what we do not know. For now, let the concept of chaotropicity settle into the background of your thinking. It is an unusual idea, the idea that water can be present and yet unavailable, that a pool can be wet and still be, chemically, a desert. That life, which requires water, can find itself excluded from a place that has plenty of water, not because the water is absent, but because the water has been recruited into a kind of chemistry that makes it useless for the purposes of cells and proteins and the rest of the molecular apparatus we call biology. Think of it this way, if it helps to have an image. Imagine a library full of books. The books are there, the library is full. But every book has been locked in a glass case, and you do not have the key. The information is present but inaccessible. Chaotropic brine is something like that for water. The water molecules are present, measurably so, you can weigh them and count them, but they are tied up in interactions with the magnesium and calcium ions in ways that take them out of play for biology. They are water, but they are not, in the functionally relevant sense, available, and life needs water to be available, not just present. This is a refinement of the earlier, simpler rule. The earlier rule was, where there is liquid water, there might be life. The refinement is, where there is liquid water with sufficient activity, with enough molecules free to participate in the chemistry of living cells, there might be life. The refinement matters enormously when you are trying to assess other planets and moons, because the refinement means that water alone is not the signal you want. You need to know what is dissolved in it. You need to know its chemistry, and specifically whether the chemistry has pushed water activity below the threshold that biology can work with, or has introduced chaotropic agents that disrupt what water activity remains. The Danakil Depression and the Dallol hydrothermal field within it contains, in various pockets and pools and chimneys, examples that span the relevant range. Some pockets, it appears, are within the range where life can function, where the water activity is low, but not impossibly low, where the acid is harsh, but the temperature is slightly reduced by the local microgeography, where the chaotropic load is present but not at its peak. In those pockets, if the Kavalatsi team's analysis holds, nanohaloarchaea find a way. They cling to the mineral surfaces. They exist in populations that are sparse by the standards of comfortable environments, impoverished in diversity compared to what you would find in a pond in a temperate forest, but biologically present in the measurable sense. Other pockets, the ones Elpez-Garca's team focused on, appear to be past the edge, past the water activity threshold, past the chaotropic tipping point. Boiling and acid and salt and magnesium-rich brine all stacked on each other until the combined effect is something life. On this planet, in every form we have found it, cannot overcome. Those pools are wet and hostile and chemically lively and biologically empty. Not by accident, not because no organism has found them yet, but because the chemistry itself forbids habitation in the same way that a room at 400 degrees Celsius forbids habitation. Not by exclusion, but by physics and chemistry operating at their limits. What makes this significant is that the two sets of pools, the inhabited ones and the genuinely sterile ones, sit in the same hydrothermal field. They are separated by distances a person could walk in a few minutes. Their chemistry differs by gradients that instruments can measure and that the human senses cannot distinguish. You could stand between them and not know, without the instruments, which was which. And the difference between them is the difference between somewhere life can hold on and somewhere it fundamentally cannot. This is not a failure of life, it is a finding about life. It is the location, or near enough to the location, for current instrumentation of a boundary that biology has been unable to cross, despite billions of years of trying. A boundary that, if it is where the data suggest it is, applies not only to this basin in northeastern Ethiopia, but to every environment in the solar system, and beyond that assembles similar chemistry. The boundary is portable. It travels with the conditions. Wherever you find the same combination of chaotropic magnesium brine and extreme acid and boiling heat and low water activity, the boundary will be there too. This is why astrobiologists drive to Dallol with their gas monitors and their sealed vials. Not to confirm that life thrives in extremity. Life thriving in extremity is already well documented in dozens of other locations: hot springs and deep-sea vents and acid mine drainage and salt flats. The well-documented story has been told. Dallol offers something rarer, the chance to study extremity past the point where life can follow, and to do so in a place where the chemistry mirrors the chemistry we are finding on other worlds. If Europa's subsurface ocean has high magnesium concentrations from long interaction with its silicate seafloor, the water activity constraint applies. If ancient Martian brines in the deep subsurface carried the sulfate and iron oxide fingerprint that surface mineralogy suggests, the chaotropic question applies. If Enceladus's ocean, warm at its hydrothermal floor and cold above, stratifies into chemistry that shifts across gradients, the question of where along those gradients the water activity threshold falls becomes critically important. Dallol is where we can begin to answer those questions with instruments in hand, rather than inference from orbital spectroscopy. There is something almost restful in the scale of it, if you let the night carry the thought instead of letting it press against you. The researchers with their equipment are doing something that has no practical application in the immediate sense, no cure for anything, no resource to extract, no technology to develop. They are drawing a boundary on a map of the possible. They are defining, as precisely as current instrumentation allows, the outer edge of the zone where life as we know it can function. And they are doing it in a desert in northeastern Ethiopia, in a place most people will never visit, at the edge of a hydrothermal field where the colors are alien and the chemistry is, in some pools, genuinely lethal, and where the question they are trying to answer applies to planets and moons, the nearest of which is hundreds of millions of kilometers from the soil they are kneeling on. The mineral chimneys continue to grow. The hydrothermal fluid continues to rise. The nanohaloarchaea, if they are there, continue to do what they do, which is metabolize slowly in the narrow zone where the chemistry still permits it, reproducing slowly, holding on. And the other pools, the ones where the chemistry has crossed the line, continue to bubble and circulate and exchange minerals with the atmosphere, absolutely devoid of anything that could be called alive, not because life has not reached them, but because life cannot hold there. Both facts are true at once, in the same hydrothermal field, under the same sun, beneath the same stars. The inhabited and the genuinely sterile side by side. Let the image be this, as you settle into whatever position the body has found for sleep. A field of pale mineral towers in the darkness, their surfaces encrusted with salt and sulfur, their bases warm from the fluid that built them. Around the bases, in the narrow zone, where the fluid has cooled slightly and the chaotropic chemistry is fractionally less intense. Organisms so small they are invisible to any unassisted human sense are present. Not thriving, not abundant. Present, doing what living things do, which is persist until the conditions that permit persistence stop permitting it. A few meters away, a pool. The same basin, the same sky above it, the same geological setting. But the water in the pool is a degree or two hotter, and the magnesium concentration is slightly higher, and those degrees and that concentration tip the chemistry past the boundary. The water molecules are there, but not available. The protein-folding machinery that life depends on cannot function in these conditions. The pool is, in the most literal biological sense, empty between the two. A gradient that instruments can measure and that represents something important. The exact location of a limit. Not a dramatic wall, not a sudden cliff, but a gradient, and somewhere along that gradient, somewhere that two research teams still disagree about, because the data are fine enough that interpretation matters, the possible becomes the impossible. That gradient is what makes this desert a laboratory. That gradient is what makes every satellite image of Dallol sent to planetary scientists more than just a pretty picture of coloured pools. And that gradient, measured and argued over and refined by researchers who drive here in convoys and fill vials at the edge of boiling acid, is one of the most important things any place on Earth has to offer the question of whether the universe is inhabited beyond this small blue world. The night is deep now. The temperature has dropped enough that the rock holds the warmth of the day, but the air above it has cooled, and the stars are very clear at this latitude and elevation, or rather at this below elevation, this negative altitude, this basin floor that sits lower than the sea that cannot reach it yet. The chemistry in the pools does what chemistry does in darkness, which is the same thing it does in daylight, unchanged. The organisms in the chimneys, if they are there, do not know what time it is. They do not have a concept of night. They persist at the pace that the chemistry permits, which is slow, and the dark is no different from the light to them. You, on the other hand, have eyelids, and the particular kind of mind that can be stilled by the weight of large ideas when those ideas are presented gently enough and at the right pace. The idea that some water is too hostile for life is a large idea. The idea that the same desert contains both a place where life clings and a place where it cannot, separated by walking distance, is a large idea. The idea that researchers have come from Bologna and Madrid and Paris to find and measure that boundary because it applies to Europa and Mars and every other wet, hostile place in the solar system is larger still. Let these ideas be present without pressing. Let them float in the warm dark the way the mineral chimneys float in the brine, passive, patient, not asking for your attention, simply there. The gradient exists whether you think about it or not. The boundary is where it is, whether it has been fully measured or not. The archaea in the chimneys, if they are there, are persisting at this moment, in this darkness, in a way that does not require your awareness to continue. The science does not stop when the scientists go home. The dispute does not resolve when the journals close. The pools and the chimneys and the gradients and the thresholds remain exactly as they are. Doing what they do, holding their chemistry steady, asking the question that the researchers have come to answer: is this water available enough for life? Have we reached the edge? Sleep now if the body is ready. The question will still be there, and so will the disagreement, and so will the basin with its mineral towers and its boiling pools, and its neon colours, and its extraordinary, almost unbearable scientific importance. All of it patient in the way the mantle plume is patient, which is to say not patient at all in any human sense, but simply there, unchanged, waiting for the morning when the next argument can begin. The dispute itself is worth carrying into the dark with you. Not the kind of dispute that presses on the mind and won't let it rest, but the kind that simply stays, the way a question stays when you've accepted that the answer is still being assembled somewhere by people who know far more than you, in a language of chemistry and molecular structure that most of us will never fully speak. You can hold the shape of the disagreement without holding its tension. You can let it float. Here is what happened in the simplest terms available. In 2019, two separate teams of scientists published two separate studies about the same patch of ground in the Danakil Depression. They were looking at the same springs, the same hydrothermal field at Dallol, the same extraordinary chemistry of acid and salt and heat. They were asking the same fundamental question: can anything live here? And they arrived at answers that pointed in almost opposite directions. This is not a common thing in science. Usually, when two experienced, rigorous teams study the same location using careful methodology, they converge on a version of the same conclusion, even if they differ on the details. What happened at Dallol was rarer than that. The disagreement ran deep enough that it was published in separate journals, attributed to different teams, and the scientific community is still, as of the time this narration was written, working through the implications. Purificación El Pez Garca is a microbiologist at the CNRS, the Centre National de la Recherche Scientifique in France. She and her colleagues had been studying the extreme environments of Dallol for some time, collecting samples, running controls, trying to understand what kind of life, if any, was doing what. Their 2019 paper appeared in Nature Ecology and Evolution, one of the more prestigious venues in the field. The finding, stated plainly, was this: in the hottest, most magnesium-rich pools at Dallol, the ones where the chemistry is most extreme, where the combination of low water activity, chaotropic magnesium and calcium chloride salts, extreme acidity and high temperature all stack together. Those specific pools appear to be genuinely sterile, not just difficult to inhabit, not just sparsely inhabited. Sterile, nothing living. A real physical, chemical limit, the kind that life cannot negotiate around, no matter how inventive its adaptations. The El Pez Garca team was careful to say that this did not mean Dallol as a whole was without life. Other areas, with less extreme chemistry, were different. But the most hostile pools, the ones that look the most beautiful in photographs, with their neon yellows and their almost surgical acidity, those pools had crossed a threshold that life, in their analysis, cannot cross. The water was there, the temperature was brutal, but not without precedent in the broader world of extremophiles. What pushed those pools over the edge was not any single factor, but the combination, and particularly the magnesium-rich brines that do something very specific to the molecules of life. Think of a protein, the long folded chains of amino acids that run every function in every living cell, as something like a piece of origami that has to hold a very precise shape to work. The fold is everything. Change the fold and the protein stops working. Chaotropic salts, like the magnesium chloride brines at Dallol, are essentially molecular disruptors. They interfere with the forces that hold the fold in place. In ordinary water, at ordinary concentrations, the water molecules themselves help maintain the structure of proteins and DNA, participating in a kind of molecular scaffolding. In brines saturated with chaotropic salts, that scaffolding dissolves. The proteins unfold. The DNA loses its integrity. The cellular machinery stops. And this happens not because the temperature is too high or the acidity too great, but because the water itself, though technically present as liquid, is no longer chemically available to support the architecture of life. This is what water activity means, not whether water exists, but whether it exists in a form that life can actually use. In some of Dallol's pools, the answer appears to be no. That is a remarkable thing to say about any place on Earth. The planet has thrown enormous variety at life, and life has, over 4 billion years, responded with an equally enormous variety of solutions. But Elpez Garca's team was arguing that here, in some of these pools, the stacking of simultaneous extremes had finally found a combination that could not be solved. Not yet. Possibly not ever, not by Earth life as we understand it. A genuine edge. Then there is the team led by Barbara Cavalazzi at the University of Bologna, working with colleagues at the Centro de Astrobiologia in Madrid. Their 2019 paper, published in Scientific Reports, also examined Dallol's mineral structures, the chimneys and terraces, the precipitated towers of salt and silicate and iron compound that grow from the hydrothermal fluid as it rises and meets the surface. And within those structures, they found something. Ultra-small microbial cells, nanohaloarchaea, a type of organism belonging to the archaea domain, the ancient lineage of life that branched away from bacteria and from the ancestors of everything else very early in Earth's history. These nanohaloarchaea were embedded in the mineral fabric of the chimneys themselves, not floating in the open pool water, but tucked into the solid structure. Persisting in what appeared to be a real biological signal, cells with the morphology and chemistry of living things, preserved in rock that was still actively forming. The Cavalazzi team did not claim that life was thriving in the most extreme pools. They were precise about what they found and where. But they did frame the finding as evidence that the mineral chimneys of Dallol, those actively growing precipitate towers rising from the brine, could harbour microbial life, and that the site, as a result, functioned as a genuine Mars analogue for astrobiology, a place where the tools and questions of planetary science could be tested against real biology in real extreme conditions. 2 studies, same year, same location. One finding genuine sterility in some pools. One finding microbial life in the mineral structures. Both published, both peer-reviewed, both authored by serious scientists with serious methods. What do you do with that? You hold the tension lightly, is one answer. You accept that science, at its best, is not a delivery service for certainty. It is a process of successive narrowing, of competing claims being tested and retested and refined over time, of one study pressing on the edge of another and then another, until the boundary becomes sharper and sharper, even if it never becomes perfectly crisp. The disagreement between Elpez Garca and Cavalazzi is not a failure of science. It is science working exactly as it should. with two careful teams looking at an astonishingly complex system and each illuminating a different piece of it. The pools are not uniform, the chimneys are not the pools. The conditions vary across the field in ways that are chemically significant. What is sterile in one location may not be sterile in another, and teasing apart which condition does what to which organism requires exactly the kind of intensive, multi-team effort that this dispute represents. What both teams agree on, and this is the point that carries the most weight for the wider question, is that Dallol sits at the edge. It is a system where the boundary between habitable and uninhabitable runs through the landscape, visibly, measurably, in space and chemistry, rather than just in theory. The disagreement is about exactly where the line falls. Both teams are tracing the same line. And the line, when both studies are taken together, is becoming more precisely drawn than it was before either of them arrived. That is the scientific value of the Danakil Depression as a laboratory. Not that it gives clean answers, it doesn't, not yet, but that it makes the question concrete in a way that a laboratory bench cannot. You can model the chemistry of extreme brines in a flask. You can run controlled experiments and vary the parameters one by one. But the Danakil Depression runs the experiment all at once, across every parameter, simultaneously, at scale, in the open air, and has been running it for hundreds of thousands of years. What it is doing in its neon pools and its mineral towers is performing the test that the astrobiologists need, whether or not any astrobiologist is present to observe it. Let the images settle. The pools holding their chemistry steady through the night, the chimneys still growing, mineral by mineral, infinitesimally slowly, building their towers out of fluid that rises from somewhere far below. The border between inhabited and uninhabited running through the landscape like a line that only instruments can read. The two teams, far away now, in Paris and Bologna and Madrid, still processing what they found, still writing and arguing and refining. All of it continuous, all of it patient. There is something here, in the dark, worth saying about the word patient. The Danakil Depression is not patient in the way a person is patient. A person waits and notices that they are waiting, counts the time, feels the pull of what they are waiting for. The basin is patient in the way geology is patient, which means it is simply doing what it does with no awareness of doing it, no counting of years, no sense of waiting for anything at all. The rifts widen, the crust thins, the magma rises, the brines cycle through their chemistry. It will all still be happening long after the scientists have finished their argument, long after the journals have published their last word on the subject, long after the buildings in Bologna and Paris and Madrid have themselves become dust. This is a different kind of time than the one human lives are measured in. And sitting with it, even briefly, in the last minutes before sleep, can do something strange and quieting to the ordinary urgency of things. Because there is another layer to the Danakil Depression that is difficult to fully absorb. A deeper story running under the one about hot springs and microbial life. A story that connects to the hot springs and the microbial life, but stretches in a different direction, forward in time rather than sideways toward Mars. In September of 2005, the ground in the Afar region moved. This is not unusual. The Afar is seismically active. Small tremors are common. The land has been restless for millions of years. But what happened in 2005 was different in scale. Over the course of a matter of days, a segment of the Afar Rift, approximately 60 kilometres long, tore open. Not metaphorically. Not gradually in the way that a slow rift, might accumulate millimetre by millimetre over centuries. The ground split open in days, driven by a massive injection of magma deep underground, a dike of molten rock forcing its way through the crust like a blade through butter, widening the crack that had been building for millions of years. The surface opened by up to several meters in places. Hundreds of earthquakes accompanied the event, some large enough to feel strongly at the surface. Others in a continuous trembling swarm that registered on seismometers across the region. Geophysicists were paying attention. Atalay Ayele at the Addis Ababa University was among those tracking the seismic record. Tim Wright at the University of Leeds was using satellite radar data, a technique called INSAR, which measures tiny changes in the surface of the Earth from space by comparing radar images taken before and after an event, to map exactly how much the ground had moved and where. Cindy Ebinger, then at Royal Holloway, University of London, was part of the broader network of researchers documenting what had happened. Together, they and their colleagues assembled one of the most detailed pictures ever produced of what is called magmatic rifting, the process by which a continent breaks apart, not just by being pulled from either side, but by being injected from below, the crust wedged open by rising magma that crystallizes into new rock once it cools. What made the 2005 Dabbahu event, sometimes called the Manda-Hararo rifting event, so scientifically extraordinary was not just its size, but what it was. This was ocean floor spreading. Not happening at the bottom of the ocean, where such things have been observed and measured for decades and are relatively well understood, but happening on dry land, in a place where human beings could walk up to the edge of the rift and look in. Ocean floor spreading is the process by which the mid-ocean ridges, the vast underwater mountain ranges that run through all of the world's ocean basins, continuously produce new crust. Magma wells up from below, forces the existing crust apart, cools and solidifies, and in this way the ocean floor is continuously manufactured and the ocean basins slowly widen. It is one of the fundamental mechanisms of plate tectonics, operating everywhere beneath the sea, and it had never before been witnessed at the surface in quite this way, with this clarity and at this scale. The Afar Depression is the exception. Here the ridge is on land, exposed, because the basin has sunk so far below sea level that in some areas it approximates the elevation of a seafloor that hasn't yet been covered by water. The 2005 event let Ayele and Wright and Ebinger watch, in real time, a process that normally happens in darkness at the bottom of the ocean, kilometres below any diver. They could correlate the seismic tremors with the surface deformation. They could measure the dike geometry from the satellite data. They could map in extraordinary detail what had happened and in what sequence. It was, as one researcher described it, like having a window into the mid-ocean ridge, and the window was 60 kilometres wide. And here is the thing about that window: it is still open. The Afar Rift is still spreading, still widening, still injecting new material from below. The rate is slow on a human timescale, roughly 1 to 2 centimetres per year along the rift, but it is fast on a geological one, and it has been going on for millions of years already. What it is building, incrementally, centimetre by centimetre, across the long, unthinkable corridors of geological time, is a new ocean. This is not speculation. It is the expected outcome on current trajectories of what is happening beneath the Danakil Depression at this moment. The Nubian plate and the Somalian plate are separating. The Arabian plate is moving away from both. As they do, the basin between them sinks. Eventually, and eventually here means millions of years, tens of millions, a span of time that makes the existence of our entire species look like an afternoon. The Indian Ocean will flood in. Water will cover the Dallol hydrothermal field. Water will cover the salt flats where the Afar caravans still move. Water will cover the lowest point at Lake Asile, already well below sea level, already technically closer to the ocean floor in character than to a normal desert valley. Fresh basaltic crust is already forming beneath the depression, the same type of crust that underlies every ocean basin on the planet. The Danakil Depression is not just above a plate boundary. It is in the process of becoming the floor of an ocean that doesn't exist yet. Let that be a slow thought, not an urgent one. The ocean that will one day cover this basin is not something any human being will live to see. It is not something any organism alive on Earth today will see, unless life itself has a span we cannot currently imagine. It belongs to a future so remote that it is essentially fictional from where we sit, outside the range of any normal human concern, beyond the edge of any recognizable timeline. And yet it is real. The process is underway. The measurements confirm it. The ground is moving at 1 to 2 centimetres per year, and it has been doing so for millions of years, and it will continue for millions more. And at the end of that accumulation, there will be water where the salt flats are, and seafloor where the neon springs bubble, and nothing of what any visitor to Dallol today experiences will remain above the surface. There is a specific quality to the feeling this produces, and it is not fear or urgency or grief, exactly, though it touches something adjacent to all three. It is the feeling of being reminded of scale in a gentle way, of understanding for a moment that the ground beneath you is not stable in any final sense. It is merely stable on the timescale of your life, and your life is very short, and the ground has a longer story than the one you are present for. Not a frightening thought when held softly in the dark, more like a recalibration, a loosening of the assumption that the present arrangement of continents and basins and climates is the permanent one, the real one, the one the planet intends. There is no intended arrangement. There is only the arrangement that exists right now, for now, in the middle of a much longer process. And there is one more layer, one more piece of the story that belongs to the same basin, the same sediments, the same slow rearranging ground. The Afar region is where we found some of our oldest ancestors. In 1974, in the Afar, at a site called Hadar, a team of paleoanthropologists excavating the sediments of the depression found something small and old and completely unexpected. A partial skeleton, fossilized female, belonging to a species called Australopithecus afarensis. The name given to this individual was Lucy, and she was approximately 3.2 million years old. She stood upright, she walked on 2 legs, she had a brain smaller than ours and a face quite different from any human face today, but she was undeniably on the lineage that led to us. And she was found in the ground of the Afar region, preserved in sediments laid down by the same ancient geological processes, the rifting, the flooding, the evaporation, the accumulation of sediment that built everything else in the basin. Lucy was not alone in the evolutionary record of the Afar. Also from Afar sediments came a find designated Ardipithecus ramidus, known informally as Ardi, whose partial skeleton was announced in 2009, but whose fossils had been painstakingly excavated and prepared over many years before that. Ardi was older still, approximately 4.4 million years old. Where Lucy represented a species that walked upright with some confidence, Ardi was an earlier stage, a creature that moved through trees and along the ground in ways we are still working to understand, a glimpse of an even earlier moment in the branching that eventually produced human beings. Both of them, here, in the Afar, in the same basin that holds the world's hottest inhabited temperature record, and the pools with near zero and negative pH, and the salt chimneys where nanohaloarchaea may or may not persist at the edge of what chemistry allows, and the lava lake at Erta Ale that has been burning since before any living human being was born, and the rift that split 60 kilometres open in 2005. And the proto-seafloor that will one day be covered by a new arm of the Indian Ocean. There is a word for the feeling of recognizing that a single place holds multiple vast things at once, and the word is probably not a single English word. Something between awe and a kind of vertiginous wonder, the sensation of a perspective shift that the mind cannot fully accommodate, but attempts anyway. The Danakil Depression is one of those places that resists simplification, not because it is complicated in a tedious way, but because it is genuinely, almost absurdly, multiple. It is, simultaneously, the extreme heat record, the acid pools at the limit of life, the hydrothermal laboratory where two teams of scientists argue about whether anything can persist. A working analogue for early Mars and for the briny oceans beneath the ice of Europa and Enceladus, the only place on land where three tectonic plates visibly diverge, a site where a new ocean floor is already being manufactured, and the ground from which we pulled the oldest bones of our own walking ancestors. Most places have one story. This one has several, and they run in different directions in time, and they are all happening in the same square of rock and salt and heat. That is not a metaphor. That is the actual situation in the Afar region of northeastern Ethiopia, if you pay close enough attention to what the ground contains. And the ground is patient in its way. It does not announce these things. The neon pools do not have signs explaining that they approximate the chemistry of early Mars. The salt chimneys do not signal that something may or may not be living inside them, at the edge of what life can tolerate. The rift does not make noise as it widens its centimetre per year. Lucy's bones lay in the Afar sediment for 3.2 million years before anyone arrived to find them and understand what they were looking at. Ardi's bones lay in older sediments still, undisturbed, unannounced, for 4.4 million years. The place holds all of this quietly, the way deep places hold things, without agenda, without the desire to be understood or appreciated, simply as a fact of what they are and where they are and how they came to be. This is, in a strange way, a comfort. There are things in this world and in this particular corner of it that do not require your attention to continue being remarkable. The springs at Dallol are extraordinary whether or not a scientist is crouching beside them with a pH meter and a sample vial. The new ocean forming beneath the depression is forming whether or not any geophysicist is running INSAR data from a satellite. Lucy existed for 3.2 million years before anyone knew she existed. The fact that we eventually came along to name things and measure them and argue about them is something we added to the situation. It was always extraordinary before we arrived, and it will continue to be extraordinary long after we are gone. There is a kind of peace available in recognizing that the world's most important things are not waiting for us to notice them. They are simply there. The Triple Junction, where three plates pull apart, the Red Sea Rift and the Gulf of Aden Rift and the East African Rift, all converging under one piece of ground. not waiting. The basaltic crust crystallizing from cooling magma in the depths of the rift, not waiting. The boundary between the chemically habitable and the chemically uninhabitable, wherever it falls in the gradients between the mineral chimneys and the most extreme pools, not waiting. Everything patient, in that deep, non-intentional way. Everything continuing. There is something the scientists from Bologna and Madrid and Paris and the CNRs came to understand about this place. Something that goes beyond the specific findings of any individual paper, beyond even the dispute about whether the hottest pools are inhabited or sterile. What they understood, spending time in the field, breathing through masks to filter the hydrogen sulfide and the sulfur dioxide, watching the springs change color as new minerals precipitated out overnight, is that the Danakil Depression is not an aberration. It is not a freak of geology that has nothing to teach us about anywhere else. It is an extreme version of processes that operate more quietly everywhere. The same tension between the conditions for life and the limits of life runs through every ecosystem on the planet, just usually in a register too subtle to see clearly. Here the register is turned up as high as it goes, and the gradient from livable to unlivable happens across meters instead of thousands of kilometers, and that compression is exactly what makes it useful. What the scientists are doing at Dallol, in the most literal sense, is practice. They are practicing asking the question, where does life give up? In a place where the question has a visible, measurable, negotiable answer. They are building the tools and the frameworks and the calibrated intuitions that they will need when the spacecraft eventually lands on the ice of Europa and drills through to the liquid water below. Or when the instruments on a Mars lander detect the chemistry of an ancient lake bed and we need to decide whether that chemistry could once have supported something. The answer to that question in those other contexts will partly come from this one. From these neon pools, from these chimneys, from the Elpezgarka team and the Cavallazzi team and their opposing findings and the years of work it will take to reconcile them. The deadliest desert on Earth is a laboratory for that question. That is what the title of this film was trying to say, and the saying of it deserves a moment of rest before you proceed into sleep, because it is a genuinely large idea dressed in the modest clothes of a geological feature. The place that holds the heat record and the acid record and the salinity record is also the place that has most precisely defined what inhabitable means. The most extreme environment on the planet is also, in a specific and technical sense, one of the most useful. The place that could kill you fastest is also the place teaching us the most about where life can and cannot hold on, across this world and possibly others. And the same ground that contains the neon springs and the mineral chimneys and the active rifts holds the bones of creatures who walked upright in the early morning of our evolutionary story, who looked out across a landscape that was already ancient, already rifting, already accumulating its extraordinary stack of geological superlatives, and moved across it on two legs, leaving no record of whether they found it beautiful. We cannot know what Lucy saw, standing in the Afar 4 million years ago, but we know the landscape was already something. The rifts were already open, the heat was already present. The volcanic features that would later become the hydrothermal field at Dallol were in some earlier stage of their formation. The Triple Junction was already doing what it has always done, pulling three pieces of the planet apart in three different directions, slow and relentless and completely indifferent to the small, upright creatures moving across its surface. And she walked. and her bones were preserved in the sediment, and they stayed there for 3.2 million years. While the world changed and the ice ages came and went, and the basin deepened and the salt thickened, and eventually human beings arrived who could understand what kind of creature she had been and what it meant, that she had walked upright, and what that walking meant for the long story of the species that eventually produced people who go to universities in Bologna and Paris and ask questions about the limits of life. There is a thread. It is long and it is thin, and it runs from Lucy's bones in the Afar sediment to the nanohaloarchaea in the mineral chimneys at Dallol, to the spacecraft being designed right now to probe the oceans of Europa. Not a straight thread, not an obvious one, but it is there, and the Danakil Depression is the place where it is most visible, where you can hold several parts of it at once and feel the whole thing vibrate with something like coherence, something like meaning, without needing to name the meaning too precisely. Let it vibrate, quietly, in the dark. The springs at Dallol are doing what they have done for hundreds of thousands of years, which is rise from below, hit the surface, cool, precipitate their minerals, build their towers, acidify their pools, colour themselves with iron and sulfur and potassium salt in shades that no painter has matched yet, and wait, not wait, simply be, in a basin that is slowly, irreversibly becoming something other than what it is. The rift is widening tonight, not in any way you could detect without instruments. 1 to 2 centimetres per year works out to roughly 600 millionths of a centimetre in the time it will take you to fall asleep. But the direction is set. The process is underway. The ocean that doesn't exist yet is one night closer to existing, which means nothing in any practical sense, but everything in the sense of what the planet is, and what it is doing, and what it has always been doing, with complete indifference to whether anyone is awake to watch. The scientific dispute, Elpez Garca and the sterile pools, Cavallazzi and the inhabited chimneys, is unresolved. It will likely find some resolution in the coming years, as more teams publish more findings and the picture becomes clearer about exactly which conditions in exactly which micro-environments at Dallol support life, and which do not. When that resolution comes, it will be one of the more important findings in astrobiology in recent decades, because it will have defined, empirically, using a real natural system, the outer boundary of what Earth life can tolerate. And that boundary is the reference point for every future question about life on another world. For now, the boundary is approximately where it has been established by two careful teams looking at the same ground and disagreeing with each other in the productive way that science allows. Somewhere between the mineral chimneys, where nanohaloarchaea may persist, and the most extreme magnesium-rich pools, where water activity drops low enough and chaotropic chemistry runs strong enough that the folding of proteins becomes impossible. Somewhere in that gradient. The exact coordinates are still being determined. The instruments are still being calibrated. The samples are still being analysed. And the springs are still rising and cooling and depositing their minerals and building their towers and running their chemistry, unconcerned, as they have always been, whether anyone has determined exactly where the boundary falls. The salt flats are quiet tonight, the way they are always quiet, which is absolutely. In the particular absolute silence of a hyper-arid basin with no trees and no insects and no running water and almost no wind at this hour. The stars over the Danakil Depression are extraordinary. because the air is so dry and so clean of moisture that the sky is almost perfectly transparent, and you can see more stars from here than from almost any inhabited place on Earth. And this is another superlative the basin has not advertised. Erta Ale is glowing, roughly 90 kilometres to the south, its lava lake doing what it has done since at least the early years of the 20th century, which is hold its pool of molten rock at the surface and let it circulate and crust over and break apart and circulate again, breathing in its way. The lake is not patient. It is simply continuous. It does not rest. It is, in the way that a fire does not rest, always in motion at the molecular level even when it looks still from a distance. It glows in the dark over the Afar, a light nobody asked for, a warmth nobody needed, a signal that the mantle is close to the surface here and that the planet beneath this particular desert is more alive, more energetically unstable than almost anywhere else you could stand. The Afar mantle plume pushes up from below, hot rock rising like a slow upwelling, thinning the crust, feeding the volcanism, driving the rifting, making the ground warmer than it would otherwise be, contributing its heat to an already hot system. It has been doing this for millions of years. It will continue. The Afar people are asleep in their settlements tonight, or some of them are. And some of them are moving through the basin with their camels, as they have moved for centuries, cutting the salt from Lake Asale in rectangular blocks, a mole, loading the slabs onto the animals, beginning the long walk out of the depression and up to the highlands where the salt will be sold. The salt that was once currency, that once paid debts and bought grain and settled accounts in the Ethiopian highlands, and that now is traded in a market that is less exotic and more ordinary, but still runs on the same geological resource, the kilometres thick evaporate deposits laid down by a sea that flooded and evaporated and flooded again over hundreds of thousands of years. The salt is the sea. The sea that was here before the basin was this deep, before the rifting had proceeded this far, before the Red Sea floods that repeatedly covered the depression had been succeeded by the current arid phase that makes it look and feel like a desert rather than a seafloor. The salt remembers, not in any conscious sense, but in the chemical record, in the layers, in the isotopic signatures that geologists can read to reconstruct the history of floods and evaporations and floods again. The ground holds its own history, encoded, patient, available to anyone with the right instruments and the time to read it. This is the last thing to carry into sleep. Not as a problem or a mystery requiring resolution, but as a simple, grounding fact about the world. The ground holds its history. Every landscape holds more than it shows. The places that look dead often hold the deepest records of life, and the places that look empty are sometimes the fullest of evidence. A basin that seems like a wasteland, too hot, too acidic, too saline, too remote, turns out to be a laboratory for the limit of life, and a nursery for the ocean that doesn't exist yet, and a cemetery where our oldest walking ancestors were preserved for millions of years, waiting to be found. The deadliest desert on Earth is also, in ways that take a long time to see and longer to fully hold, one of the most alive. Alive in the sense of process, of ongoing transformation, of questions that are still open, and sciences that are still being built, and futures that are still being assembled, centimetre by centimetre, in the dark beneath the salt. And you are here, at the end of a long narration, carried through the acid pools, and the mineral chimneys, and the bones in the sediment, and the rift opening in the night, and the glow of Erta Ale on the horizon, to a place of rest. The basin will be here when you wake. The question will still be open. The springs will still be rising. The Elpezgarka team and the Kavalatsi team will still be somewhere on different sides of a productive argument, sharpening the boundary that defines what life can and cannot do. The rift will have widened by another fraction of a millimetre. Lucy's discovery at Hadar will be 49 years old and still extraordinary. The lava lake at Erta Ale will still be moving. None of it needs you to be awake for it to continue. Let the Dallol springs hold their neon chemistry through the night without you. Let the Afar rifts do their slow work. Let the salt remember the sea. Let the scientists in their distant offices work through their data, and let the dispute find its resolution in whatever time it needs. And let the new ocean wait in the deep future where it belongs. The weight of all that extraordinary ground, all those superlatives, all that contested borderland, all those locked in millions of years, does not rest on you. It rests on the mantle plume, 3 kilometres down, warm and patient and entirely capable of bearing it. Tie off here at the Wisdom Docks. The tide will wait till morning.